Alright guys, with this lesson, lesson 14, we're modeling relationships with a line. We're diving back into what scatter plots really are and what we really do with scatter plots, because albeit, yeah, it's nice to have a graph with data and to be able to look at things, but we have to be able to use it. If we can't use it, it's pretty much useless. So today we're going to be talking about lines and how we can fit an equation of a line or a line itself into a scatter plot. So it says, example 1, using a line to describe a relationship. Basically what we have are shoe lengths and heights. So 10 people, their shoe length, and their height. Now this is the actual data. Alright? One thing I want to make clear throughout this lesson is these coordinates. So these coordinates are the actual data. And the term actual is really what I'm focusing in on. And that's going to be more important later on, but just make sure you understand that these coordinates are the actual data. And we see, if we just analyze it real quick, well, as my shoe length increases, as it goes from 11.25 to 12 to 12.5 to 13, it seems that the height of the people generally increase. And this makes logical sense because typically, if you have a larger shoe size, that means you're somewhat taller. So in number 1 it says, is there a relationship between shoe length and height? Now remember guys, relationship, one thing we're going to call this in this chapter and for the rest of the time we talk about math is correlation. So is there a correlation between shoe size and height? And yes, there is a correlation between shoe size and height. As one increases, the other one does increase. So again, if we want to be more specific, we can also say there is a positive correlation between shoe length and height. Shoe length and height. If we move on, it says, how would you describe the relationship? Do men with longer shoe length tend to be taller? And we're going to call this yes. There is a weak positive correlation. If we go back to the last lesson where I taught you the difference between weak, strong, positive, and negative correlations, a weak correlation means the data points are somewhat spread out, but you can still tell that there's a relationship between them. So if we look at these data points, yes, these data points are more spread out. If they were more condensed in a straighter line, we would call that a strong correlation, but the fact that these are kind of spread out, we're going to call this a weak correlation. But again, it is still positive because it's going up. If it was negative, it'd be going down. Now, second problem. Example 2. Now, basically, in example 2, it tells you what we're doing with the scatter plot. We're going to be fitting a line to the scatter plot. So it says when two variables, x and y, are linearly related, you can use a line to describe their relationship. That's huge. And this is what I was talking about last lesson, is these data analysts gather thousands and thousands and thousands and hundreds of thousands of data points, and they make them fit a certain algorithm or a certain regression. Whether it be linear, exponential, quadratic, or some other type, they still make it fit a certain type of equation. Now it says you can also use the equation of a line to predict. That's also the big thing here, guys, is predicting. We don't just do this just to do it. We do this to make informed predictions. So again, if we have an equation has an x and a y, we can plug numbers in for x, get our y, or we can plug numbers in for our y and get our x. So it says, for example, the line y equals 25.3 plus 3.66x might be used to describe the relationship. If you're wondering where that came from, guys, I'm going to show you later on in this video, but basically, that is the line of best fit. That is the linear regression right there. And how they determined this was by using a calculator, which I will show you soon. Again, that's just not a random line. That is actually what this data is saying. So it says to predict the height of a man with a shoe length of 12, you would substitute 12 for x. Remember in this problem, x is shoe length, y is going to be height. So if they give us a shoe length of 12 and x is shoe length, all you have to do is, well, plug 12 in for x, like they do right here, and then do 25.3 plus 3.66 times 12, and that equals 69.22. So what they're saying is, if a man has a shoe length of 12, that means they should have a height of 69.22. It's not they will have a height, because again, nothing is 100% certain. With this data analysis, we're not saying it will happen. We're saying it could happen, or it should happen. We're not saying it will. So again, the predicted height is 69.22. Now, again, we'll come back to that. We have two lines below. We have a scatter plot which has the same one from before, which has two lines. Y equals 130 minus 5x. That's the black line here. And then 25.3 plus 3.66x. That's the blue line here. It says, which of these two models does a better job describing shoe length and height? Explain your reasoning. So, if I'm looking at this, you guys can pause the video here and try to figure it out for yourselves. Otherwise, it's pretty straightforward. We know from before that we said this has a weak positive correlation. Meaning, as x increases, y increases. If I'm looking at these two lines, well, the blue one is clearly increasing, but this black line is decreasing. Now you may be wondering, Mr. Z, that black line goes through 2 points though. That blue line goes through no points. That may be true, but at the same time, that black line is decreasing. So, I'm going to say y equals 25.3 plus 3.66x does a better job because of the fact that it's increasing with the data. Increases with the data. Whereas the black line decreases. We already said this is a weak positive correlation. There's no reason why our equation that we're trying to use to model this data to decrease. It has to follow what's going on with the problem. So it says one of the men in the sample has a shoe length of 11.8 and a height of 71. Circle the point in the scatter plot in exercise 3 that represents this man. So again, we're trying to figure out a shoe length of 11.8 inches and a height of 71. So if I'm looking, alright, well, it has to be between those two. And it looks like I have two coordinates in that area. But I need a height of 71, which is all the way up here. Well, the only point that is even close to being there is right here. So again, that is a coordinate of 11.8 and 71, because again, this is x, this is y. That means I'm looking for the coordinate 11.8, 71. Number 5. Suppose that you do not know this man's height, but you do know his shoe length. If you use the model, what would you predict his height to be? If you use the other model, what would you predict his height to be? Now, we already have our two models, and we've already discussed why the first one fits better than the second one. So, I'm still going to go through the process of what it looks like using the second one, but you'll see quickly why it doesn't work out. So, again, this right here is our shoe length, and our shoe length is 11.8, which is x. So, y equals 25.3 plus 3.66 times 11.8. So, in order to do this, we have to take our calculator, which I have, and I'm going to do 25, I'm going to turn it on first, 25.3 plus 3.66, I did that wrong, I did all of this wrong, 25.3 plus 3.66 times 11.18, or 0.8, sorry, and that's going to be 68.488. And again, that's the predicted value. This is the predicted value. It's not his actual height. It's the predicted height based on the model we have. Now, if we use the second model, y equals 130 minus 5 times x, well, x is 11.8. Now, instead of pulling that graphing calculator up, I'll just do it on the one I have beside me. And I'm going to have 130 minus 5 times 11.8, and I'm going to get 71. Now it says, if you use the model, what would you predict his height to be? We would predict his height to be 71. So if you take a look at his predicted versus his actual, the second model actually gets it on the head. Like, it says it's 71, and that's what his height should be. And if we scroll back up to the line, that point is actually on the black line, like we said earlier. So this is why checking a linear regression, checking an equation can be flawed. Because if you just check one point, you can see that, oh, this line is super, super close, or it's dead on, where the other line isn't as close. But in reality, that black line isn't close to, well, 8 points on the graph. It's only close to 2. So again, when you try to check your work, if you try to check your equation that we're eventually going to create, you can't just pick one point, alright? It does say it's dead on, but again, we know from earlier that that equation is actually false. So, again, his predicted height should be 68.488. Which model is closer to the actual height of 71? Is that model a better fit to the data? Again, we already talked about it. Y equals 130 minus 5x is what is closer, but it's not a better fit. Again, we already talked about how it's close to 2 coordinates, but it's not close to any of the other coordinates. Two of our coordinates. And this is a big thing behind lines of best fit, is that when you create these lines of best fit, you want to make them so they're close to the majority of the points. For example, if I'm taking a look at this black line, it's dead on 2 points. One circled, the other one circled here, and it's kind of close to this point. But look at all these other points on the outskirts. It's not close to it at all. Now, on the other hand, if I erase this and we look at the blue line is close to this point, this point, this point, this point, this point. I'll even say it's close to this point. Now, yeah, it's not that close to these 2 points, but it does a much better job overall with the data than the first line did. So again, that's why when you're making a line of best fit, you're not going to make every point. You're not going to hit every point, and you're not going to make it fit the data perfectly. Nothing in the real world is going to be perfectly linear. Okay? But you want to pick the best fit model. That's why it's called a line of best fit. So, again, is there a better way to decide which of the 2 lines provides a better description and relationship rather than comparing the predicted value to the actual value for one data point in the sample? Yeah. Don't just use one data point. Use all data points. Or graph them. And look. Alright guys, example number 3, residuals. Now, there is a way to put how close something is to the line in a mathematical number, and that's called a residual. So it says one way to think about how useful a line is for describing a relation between 2 variables is to use the line to predict the y value for the points in a scatter plot. These predicted values could then be compared to the actual values, because again, if we look back at our line, our predicted values is our actual graph. Our actual values are the coordinates. So that black line hits 2 predicted values dead on. But look at how far away the other coordinates are. They're extremely far away. Now, on the other hand, the blue line may not hit any coordinates, but look how close it is to the actual coordinates. So the predicted coordinates and the actual coordinates are very, very close. So that is a very decent way to describe whether or not a line works. So it says, for example, the first data point in the table represents a man with a shoe length of 12.6 and a height of 74. If you use the line y equals 25.3 plus 3.66x to predict the man's height, you would get the following. So, if you plug in 12.6, this is the answer you'll get. Now, to find the residual, we know his predicted height is 71.42. His actual height is 74. To determine the residual, all you have to do is subtract the actual minus predicted. So I'm going to take 74 minus 71.42, and I'm going to get 2.58. Now, to give you an idea of what that means graphically, if I erase all these circles again, let's say I want to figure out the residual from this point, right here. I want to figure out the difference between this point and this point. I'll actually make it red so we can see it better. That's what I'm trying to figure out. I'm trying to figure out the difference between these 2 points. That's the residual. Now, in math, we also know the difference between 2 points can also be considered the distance between 2 points. So in reality, a residual is just the distance between the line and actual value. So that's a huge concept to understand, guys, that a residual is just the distance. So if I scroll back down, number 8, it says for the line 25.3 plus 3.66x, calculate the missing values and add them to complete the table. So what I want you guys to do now is to pause this video and then actually go through and complete the rest of the values in this table. It's just plugging numbers in for x, cranking them out for y to get the predicted values, and then once you get the predicted values, you're then able to determine what the residual is by taking actual minus predicted. So, pause the video, do it yourself, come back and check your work. I'm going to go through and write down these answers. It's going to be 68.49. It's going to be 69.95. It's going to be 69.95 again. And then the residuals are 1.05. The residual is 0.98. And that's it. Now, why is the residual in the table's first row and the residual in the second row negative and positive? Well, let's take a look. Now, if we go back to what a residual is, we said it's the difference. Now, we also said it's the distance. So think about the distance between numbers. And think about what a positive difference implies and a negative difference implies. Remember that it's also actual minus predicted. So if I have a positive residual, what does that mean? If I have a negative residual, what does that mean? Well, it can mean one of two things. It can mean that if you have a positive residual, that the actual is larger than predicted. And then on the contrary, if I have a negative residual, it means the actual is smaller than predicted. And again, guys, if I'm subtracting 5 minus 2, well, 5 is larger than 2, so my difference is positive. If I'm subtracting 2 minus 5, well, 2 is smaller than 5, so that makes it negative. What is the sum of the residuals? And why did you get a number close to 0 for the sum? Does this mean that all the residuals were close to 0? So, the sum of the residuals for this, you can add them up quickly. That's just grunt work. But if you do it, you're going to get a number around negative 0.6 if you round it. Now it says, what did you get, or why did you get a number close to 0 for the sum? And again, if we get a number close to 0, remember, a line of best fit should have an even number of coordinates above and below the line, as does our line here. We have 5 coordinates above the line, 4 coordinates below the line. And in essence, if I have 5 above and 4 below, if there's an even amount on each, they should cancel each other out. So if they cancel each other out, our sum should go to 0. So again, this number is close to 0 because the positive and negative values of the residuals balance each other out. Not all residuals are close to 0. We already know all residuals are close to 0. It's the fact that they balance each other. That's what we have to pay attention to. So again, the residuals balance each other out. And does this mean that all residuals are close to 0? No, it does not mean all the residuals were close to 0. I mean, we had negative 3.49 and 2.58. We had negative 2.515 and positive 2.51. Like, we had large residuals in the positive and negative direction. When you use a line to describe the relationship between two numerical variables, the best line is the line that makes the residuals as small as possible. And again, best line's also called the line of best fit. So it says if the residuals tend to be small, what does that say about the fit of the line to the data? Again, the smaller the residuals, that means the shorter the distance between the predicted and the actual. The shorter the distance, it then implies that our line is super close to the coordinates. If our line is super close to the coordinates, that means this line is pretty good. It's a pretty good fit. So again, this says that the line is a good fit. Again, if the residuals are small, that means the distances are small. If the distances are small, that means the coordinates are close to the line. If the coordinates are close to the line, that means our line is a pretty good fit. The most common choice for the best line is the line that makes the sum of the squared residuals as small as possible. Add a column to the right table and add a column on the right to the table in exercise 8. Calculate the square of each residual and place the answer in the column. So, again, you guys can pause the video real quick. This is just grunt work, but I'm going to plug the answers in very quickly, so pause the video, do it yourself, and then check back with your answers. But if we add another column and call it squared, and if we square each residual, we're going to get the following numbers. We're going to get 6.65, we're going to get 12.18, 1.10, 0.57, 0.90, 0.96. We're also going to get 4.62, 0.90 again, 0.33, and 6.30. So, it says, why do we use the sum of squared residuals instead of just the sum of the residuals without squaring? Hint, think about whether the sum of the residuals for a line can be small even if the prediction errors are large. Can this happen for squared residuals? Now guys, this is a huge concept to understand, and it may take another time or two listening to my explanation, so I'm going to give it a go, and we're going to see if we can kind of get what's going on. So basically it's saying this: would it be beneficial to add up our residuals or add up our squared residuals? Which one's a better indicator at the line of best fit? Now your immediate response may be like, oh, Mr. Z, just add up all the residuals. If it's close to 0, we're good. And where that may be true, if we take a look at our graph again, which is now all the way up here, notice some of these points. This point that I'm about to circle in blue is kind of not close to the line. But if we just add up our residuals, this point along with this point pretty much balance each other out. So even though our line of best fit may be close to the data, these two large points one in the negative direction, one in the positive direction, will balance each other out. That won't be reflected in our number because, again, a large negative and a large positive will equal 0. Just like a close negative and a close positive will equal 0. But think about it and look at our table we just created. If we look at our squares, first off, whenever you square a negative, you get a positive. But notice what happened. With the residuals that were not between -1 and 1, what happened to their squared term? Well, 2.58 squared is, what? That's large. That's also large. That was not so bad. Well, that got bigger, and this got bigger. But look at the numbers that are between -1 and 1. The numbers very close to the line with small residuals, they got even smaller. So whenever we squared small numbers, we got smaller numbers. So in this process, it's much harder to hide bad residuals. Because, I mean, if we offset this -3.49 and this 2.58, those pretty much balance each other out. But when you square the residuals, that doesn't happen. They're all positive, but the smaller residuals become even smaller, the larger residuals become even larger. So it's harder to hide. So basically what I'm trying to say, and bear with me as I go through this, is if you just add all the residuals, positive and negative residuals can affect one another. And you can get a small sum even if the residuals are large, if they're big. But squaring the residuals gives positive values that still reflect how far the data points are from the line. So again, when you square them, there's no balancing out. So when you add residuals, positives and negatives balance each other out. No matter the error. Whoops, the error. But when you add sums together of squared residuals, it still shows the distance, but they won't balance each other out, so you can still see, alright, which point is close, which one's not. What is the sum of the squared residuals for the line y equals 25.3 plus 3.66x and the data for exercise 11? So if you actually go through and add up all those terms, guys, you're going to get 34.54. Now this doesn't mean anything right now to you because we have nothing to compare it to, but the sum is going to be an important part later on. Not in this lesson per se, but definitely later on as we go through this topic. So, real quick, basically all we're saying here, guys, is we're talking about a line of best fit or a regression line. These are the two things that I'm going to call this. They may call it the least squares line. That sounds completely lame to say. So instead of calling it a least squares line or a best fit line, I'm going to call it the line of best fit, which is typically known as, or a regression line, because this process that we're about to do is called regression, where we fit an equation to data points. Now, there is a way to do this in the calculator, and that's what I'm about to show you right now. So if you guys have a TI-84, whatever kind of edition you have, or 83, it's the same throughout, but as I go through it, I need to basically create that equation in this calculator. Now, here's the way to do it. First off, let me clear everything. Now, I need to put in the shoe sizes and the height into my calculator. In order for my calculator to burst out an equation, it first needs to have the data. So if I go to Stat, Edit, hit Enter, I have L1, L2, L3, basically lists. This is where you input your data. So I'm going to input 12.6, Enter, and I'm going to go through and enter all of the data. Now this may take me a while because it's a lot of data, but bear with me. 12.2, 11.6, 12.2 again, 11.4, 12.8, delete that, 12.8, 12.2 again, 12.6, and 11.8. And then, in order to scroll over, you got to put the heights. 74, 65, 71, 74, 65, 71, 67, 69, 68, 70, and then we have 69, 72, 71, 69, 72, 71. Also notice how I have the same amount in each list. We're good to go. Now, in order to create this equation, go to Stat. Now, instead of hitting Edit, scroll over to Calc. This is the page we're going to use for anything in terms of regression. Now, I need to create a linear line. Or that's repetitive. I need to create a linear equation. Now, we already know it should be in y equals mx plus b form. So if I scroll down, number 4, lin reg. We're doing linear regression. We're not doing quadratic regression yet, or cubic regression. We're doing linear regression, ax plus b. I'm going to hit enter. Now your screen may look different. Regardless, just hit enter again. Notice what happens. It tells me y equals ax plus b. It tells me that a is 3.65 and b is 25.27. Basically, that's what they gave us in the beginning of these notes. It told us, hey, your equation of the line is that line. This is the line of best fit. Your calculator does all the math for you. It calculates the residuals, and it makes it known which equation will work best. That's the equation. Okay? That's the equation. If you have to watch this video over again to go over the steps for this, please do so. Otherwise, that's what needs to happen. That's how you enter data in. That's how you get your equation. So if we go down to 15, once this is done lagging, and we'll wait, it says, assuming that 10 men in the sample are representative of adult in general, what height would you predict for a man whose shoe length is 12.5? So again, these are the shoe lengths. In order to get the heights, all you have to do is use your equation, y equals 25.3 plus 3.66x, but we know x is 12.5, so it's going to be y equals 25.3 plus 3.66 times 12.5. I'm going to crank that out in the calculator, so 25.3 plus 3.66 times 12.5, and I get 71.05. So the predicted height of someone whose shoe length is 12.5 is 71.05. You can do the 11.9 for yourself, but same concept. Now, let's talk about what these numbers mean. Now, I want to figure out what this slope is in the problem. It says, give an interpretation of the slope. Now remember, our slope is m, and it's 3.66. Now, if you recall what slope is, it's every time the x increases by 1, the y increases by, well, whatever the slope is. So in this case, x is shoe length, and y is height. So if I make this in context of the problem, for every 1 inch increase in shoe length, the height increases by 3.66 inches. And again, the height increases by 3.66 every time the shoe length increases by 1. That's what slope is. Now the y-intercept, on the other hand, if you guys remember anything, the y-intercept is typically the starting point. So anytime we talk about the y-intercept, we talk about the starting point. But think about it in this problem. Our starting point is 25.3. Now, what does that mean? At b equaling 25.3, what does x equal? What does x always equal at the y-intercept? I mean, x always equals 0. So what you're telling me is that with a shoe length of 0, the height is 25.3 inches? So basically you're telling me if you have no feet, you are 25.3 inches tall. Guys, that doesn't make sense. Unless, you know, you're someone from my first block who rhymes with Isaac. But regardless, with a shoe length of 0, the height is 25.3. Again, that means nothing. So sometimes, guys, when you create these equations, sometimes your variables won't, your intercepts won't make sense. Because you can't have a shoe length of 0. So as you go through this, guys, just be aware of these things that can happen. It is what it is. There's nothing you can do about it. It doesn't mean your equation's bad. It just means you can't use it for everything. Okay? Now, below is a lesson summary and some practice problems, guys. We will end up using these practice problems. We will not do them tonight, but I will be assigning them at a later date. If I want to go through them now, it will not hurt. But, guys, that's the lesson. If you have any questions, be sure to hit me up. Otherwise, good luck, and I'll see everyone tomorrow.